Hi, thank you for your interest in our research group. I'm Alon Greenberg Dana, and I'm excited to share with you some of our work. There's really no need to introduce this tool. ChatGPT provides fantastic insights in seconds, even though its responses are primarily probabilistic. But what if we had a platform for precise chemical insights? One that's not based on a large language model, but on real physical and chemical computations. Our group is dedicated to making this vision a reality. We aim to develop a platform where scientists and engineers can ask questions such as, what would be the shelf life of a pharmaceutical molecule? What are the optimal conditions for a specific chemical process? Or how does a reactive chemical system behave? And can we design and synthesize novel molecules for tailored applications? When thinking about how to achieve our vision, I drew an analogy of an autonomous car onto chemical engineering. An autonomous car relies on a sophisticated model to navigate the world and, importantly, can react in real time to unexpected situations, such as steering away from pedestrians and cyclists. This seamless integration of computational models with physical actions is what we refer to as a cyber physical system, CPS. The CPS platform we develop will generate predictive models based on advanced computations representing its understanding of how the world behaves. Automatically, it will test these hypotheses by conducting actual wet lab experiments. This process will provide users with critical insights into the system they care about, insights that are otherwise inaccessible to them. The potential applications are very diverse. Here are a few that we're currently working on. In pharma, we have projects focused on predicting the shelf life of drugs before synthesizing them and forecasting the behavior of lipid nanoparticles, such as those used in vaccines or targeted therapeutics, once they enter the bloodstream and interact with proteins. Retrosynthesis, applicable to both pharmaceutical and defense sectors, enables us to design synthesis pathways for specific molecules using a pool of commercially available materials. We are focused on ranking and validating these pathways to ensure their effectiveness and feasibility. Within the defense and energy sectors, we are engaged in several key projects, including optimal sustainable aviation fuel mixtures, collaborating with Boeing and local industries to predict the most effective blends in terms of ignition delay time. Satellite propulsion fuels, predicting the reactions of both classical and novel satellite fuels under various conditions. Scramjet fuels, analyzing the behavior of innovative fuels designed for scramjet propulsion systems. And novel energetic materials, searching for and developing new energetic materials with enhanced performance. Other energy-related projects include fuel cell membrane optimization, enhancing the performance of fuel cell membranes, which are critical polymeric components that must operate in harsh chemical environments, and alternative fuels, understanding the reactivity of nitrogen-based fuels and other alternative fuels such as biofuels. Also, we are looking at CO2 conversion, developing efficient pathways for converting CO2 into useful raw materials for fuels, contributing to sustainable energy solutions. We also work in soft materials, predicting synthesis pathways of flexible novel devices and 2D materials. In addition to our applied work, we are engaged in fundamental research projects, including computing accurate thermodynamic properties to enhance our understanding of complex and flexible molecules, and developing methods to efficiently identify reaction transition states, facilitating the discovery of new chemical reactions. We remain open to new collaborations, and we are eager to explore how our technology can be applied in emerging domains. The predictive models we generate are based on our fundamental understanding of chemistry. To make predictions, we need to identify all intermediate species and their cross reactions. By quantifying the interactions, we can open up a window and peek into the microkinetics of a reactive system. The big question that we ask is, how can we predict the evolution of a chemical system given known initial conditions? John von Neumann, the renowned mathematician, once remarked about modeling. "With 4 parameters, I can fit an elephant," he said, "and with 5, I can make him wiggle his trunk." His point? Tweaking parameters can make a model fit any data perfectly, but it loses the ability to predict future outcomes. The true value lies not in fitting the known, but in anticipating what's next with robust predictive models. In a tribute study in 2010, scientists took 4 complex numbers and drew an elephant with them, as you can see here, and they took the 5th one, well, you can see what they did with the 5th number, wiggled his trunk. In the spirit of John von Neumann and the tribute study here, we're also not interested in the business of fitting elephant, but rather in making predictions based on our fundamental understanding. The problem? To generate a predictive model, one needs to know many parameters, which greatly exceeds the number of parameters available to us from experiments. This is where computational chemistry comes into play, assisting us to accurately determine reaction rates without the need for extensive experiments. One major software that we use and contribute to is RMG, the Reaction Mechanism Generator, developed by the Green Group at MIT. Its job is to tell us what the relevant intermediate species are and which ones of them are significant, what the relevant reactions are and which one of them are significant, and what all the rate coefficients are, not just the significant ones, but all of them, so we can determine and differentiate between important reactions and insignificant reactions. Here's a short animation of how RMG operates. Let's say we want to understand how ethanol combusts. We start by providing the necessary inputs, as shown on the left. RMG divides the system into a core and an edge. It begins by placing the initial reacting mixture into the core. RMG then iteratively poses 2 key questions. The first question is, what are all the possible reactions in this system? RMG utilizes templates of various reaction types. It can apply these templates to molecules it has never encountered before, allowing it to predict the reactivity. The second question is, what's important out of all the possible products? It determines significance primarily based on reaction rates, identifying which products are most relevant to the system's evolution. Based on the answer to these questions, RMG continues iteratively to repopulate the edge with new species and selectively enlarge the core, refining the predictive model step by step. For every new species generated, RMG assigns accurate thermodynamic properties, and for every new reaction it identifies, it determines the corresponding rate coefficient. Eventually, after it converges, it tells us, for example, that to predict the oxidation of ethanol under the desired conditions, we need about 40 species and nearly 600 reactions. RMG identifies them for us and assigns thermodynamic properties and reaction rate coefficients. But where are all the data coming from? So we're not reinventing the wheel, and first we use pre-compiled libraries with known data where available. Next, the software uses estimations, group theory for thermodynamic properties, decision trees for rate coefficients, and machine learning for additional specific thermodynamic data. Finally, to make the model more accurate, we use quantum chemical computations for selected parameters. These quantum chemical computations are automated using a software we wrote and maintain called ARC, Automated Rate Calculator. ARC begins by discovering the 3D structures of the chemical species, and it also searches for the 3D structures of reaction transition states, as these animations show. It then executes the quantum mechanical job computations on high-performance computational servers or on the cloud, and automatically troubleshoots for any issues. Finally, it performs statistical mechanics, computations that will help us to obtain meaningful parameters for the models and process all the results. As a summary, we can see here the ecosystem of software tools for automated chemical kinetic model development. T3 stands for the Tandem tool, and it's a software for executing RMG and ARC in tandem for automated kinetic model generation and quantum chemical refinement. T3 calls RMG and sends it the directives to generate an initial model. It then performs sensitivity analysis to identify key parameters to be refined and sends them to ARC to be computed. Before sending them over, it queries a database called TCKDB, Theoretical Chemical Kinetics Database, to see if it was previously computed by anyone in the community at a reasonable level of theory. After running ARC, it will upload any computations back to the database. The cycle continues since now new and important parameters were computed, and the RMG model could now identify additional important kinetic pathways. The cycle terminates when the top sensitive parameters were all computed and are already known. This was just a taste of the applications we're working on and some of the methods we're using. There are many more exciting things going on in our group that did not make it here. If any of this was interesting for you, or if you have any questions, feel free to be in touch. Thank you.